So in the morning we heard some of the basics about real rooted and stable polynomials, and now we can start talking about some of the things you can prove using stable polynomials, and in particular the very exciting work by Marcus Spielmann and Srivastava, which really connected the worlds of stable polynomials and combinatorics and computer science and really generated all this excitement that we are witnessing here now. So, okay, before we get there, let me discuss this in a slightly more general way. We're going to talk about certain ways to prove the existence of some objects, which don't really tell you what exactly the object is. And these are the proofs that we call non-constructive or non-algorithmic. And let me do a very quick high-level overview of the kinds of methods that we know in combinatorics, which are this form. They can be broadly categorized as follows. We have the probabilistic method, which has been very successful, which is essentially you perform some random experiment, generate some random object, and then you prove using some probabilistic tools that the object has the properties that you desire. And there have been many applications of this. I can't even start to discuss them. But the important thing is that we have probabilistic tools which are useful here. Immediately this kind of proof raises the question whether you can actually find the object algorithmically, or whether you can somehow describe it explicitly. So this is an interesting question which will also come up here. Another broad category of methods is the topological one, which maybe has fewer applications in terms of how many we have, but it's also very interesting conceptually. Maybe the most famous example of topological proof in computer science is the existence of Nash equilibria, which is implied by Brouwer's fixed point theorem. Essentially, you can formulate your problem as a topological problem, and the existence of some fixed point or some topological property implies the solution to your problem. So this is another broad category of non-constructive proofs. And the third category could be described as algebraic methods. One such method is the combinatorial Nullstellensatz. And the more recent one is what we are talking about here, stable polynomials. So what these methods share is that you represent your problem as some statement about the roots of certain polynomials. And you argue about the roots, either some counting argument about how many roots there might be, or something about the location of the roots. And these kinds of arguments can yield some very interesting results. So let's call these methods algebraic. Famous examples of results proved by algebraic methods are the finite field Kakeya problem, and most relevant to this program, the existence of Ramanujan graphs and the Caddison-Singer problem. The algorithmic question is interesting in all of these cases. For the probabilistic method, I think by now it's fair to say that almost all applications of the probabilistic method have been made algorithmic, at least using randomized algorithms. So we should be careful what we mean by constructive. In some areas of mathematics, constructive might mean just having any finite time procedure that constructs the object. So here we are mostly talking from the point of view of computer science, where we want efficient polynomial time algorithms, but there's still a distinction between deterministic and randomized. Another question that comes up is whether you can actually tell that your output is correct. You might have a randomized procedure which produces what you want with high probability, but maybe it's actually hard to verify what you produced is correct. So we have to be careful about all these details when we talk about something being constructive or not. The topological method seems generally difficult to make algorithmic. One famous example is, again, the Nash equilibrium problem, where we have a proof of hardness. In some technical sense, it is hard to find a Nash equilibrium. Although it always exists, it is PPAD hard to find it. And now even in some approximate sense, it's hard to find it. So topological methods generally seem non-algorithmic. The algebraic methods are interesting. So the problems that we will talk about here, in particular Ramanujan graphs and the Caddison-Singer problem, were both very interesting questions. And the question for Ramanujan graphs has been resolved in the positive. So there is an efficient algorithm to find Ramanujan graphs, which was done by Michael Cohen. For the Caddison-Singer problem, this still remains a major open question. So now let's postpone all these algorithmic questions. That's not the point of my lecture here. And let's start talking about Ramanujan graphs. So what are Ramanujan graphs? In some sense, they're the best possible expanders. They're the best possible expanders in the spectral sense. So for a d-regular graph, we can look at the eigenvalues. There's always the top eigenvalue of d. If the graph is bipartite, you also have minus d. And then where are the other eigenvalues that will determine the expansion properties of your graph. So let's call G an n d lambda expander. If it has n vertices, it's d-regular, and all the eigenvalues except the d and possibly minus d are in the interval minus lambda. So the lambda, the smaller we make lambda, the better expander we get. So what is the best lambda that you can hope for? This is given by the Allen-Bopana theorem. Generally, you cannot hope for lambda smaller than 2 square root d minus 1. For particular graphs, for small graphs, you can have lambda smaller than this, but you cannot have an infinite family for arbitrarily large n of graphs where lambda is strictly below 2 square root d minus 1. So this is the optimal bound that you can hope for. The question is, are there such infinite families of graphs? And they exist, and the first constructions of such graphs, you have probably heard about them, were very famous results and also very difficult results. So these were 2 independent works by Lubotsky, Phillips, and Sarnak, and Margulis, and they both constructed infinite families of Ramanujan graphs where all the non-trivial eigenvalues are bounded by 2 square root d minus 1, and the degree is in the form some prime plus 1. So this comes out of some algebraic construction, Cayley graph, of some finite groups defined in terms of matrices. And the analysis is complicated. The analysis uses algebra and number theory. It's sophisticated. The name of Ramanujan comes up because the Ramanujan conjectures and number theoretic statement comes up in the proof of Lubotsky, Phillips, and Sarnak. Later this was extended to prime powers plus 1, but not all possible degrees. So a natural question here is this really a number theoretic problem? Is there something special about primes, or is there a simpler way to do it? You know, what is happening with Ramanujan graphs? This was essentially resolved, at least in the bipartite case, by groundbreaking work, which we will talk about here, by Marcus, Spielmann, and Sirastava. So there was already a procedure which was proposed earlier, which works as follows, which looks like a reasonable approach. So start with some small expander, let's say complete graph, and repeatedly perform the following operation. Let's call this the 2-lift operation. So you duplicate each vertex, and you also duplicate each edge. For each edge, you produce 2 new edges. Now you can do it in 2 different ways. So let's call this either 2 parallel edges or 2 crossing edges. For these 2 duplicated vertices, the vertices became pairs. And the edge which was between them became 2 parallel edges, which means we added u0, v0, and u1, v1. So randomly we decide to do either that or the other option, which is 2 crossing edges. u0, v1, u1, v0. Okay, so that's a random operation, which we can apply to a graph. We obtain a graph of the same degree, and the number of vertices goes up by a factor of 2. And it looks reasonable somehow. Things might mix well here because we do things randomly. It's a reasonable proposition. Bilu-Linial came up with this procedure, also proved that it works quite well. And they proved that lambda is bounded by roughly square root d log cubed d. So it's almost the right bound, except there's this polylog d. This was the state of the art until Markus Spielmann and Srivastava, who designed a beautiful proof that this actually works perfectly in the bipartite case. So if you start with the bipartite Ramanujan graphs, you always have these eigenvalues d and minus d. They stay there. But all the other eigenvalues are going to be bounded in absolute value by 2 square root d minus 1, which is the best possible bound. And you get an infinite family of graphs like this. So a beautiful result. What else do I want to say at this point? So this can be viewed as a randomized algorithm. The theorem claims that this succeeds with positive probability. But the probability might be very small. So this is not an algorithmic proof, from a CS point of view at least. Later, there was follow-up work by Markus Spielmann and Srivastava, and building up on that work, Michael Cohen showed an efficient algorithm to construct Ramanujan graphs. So that's very interesting. Maybe Nikhil will discuss it later, or it will come up certainly later in this semester. So this result has been made algorithmic. But let's talk now about the existential result. So we have this procedure which blows up the graph and does something to the edges, and we need to track the eigenvalues of the adjacency matrix. So how do these eigenvalues change under the two-lift operation? Let's see what happens. So let's call this blown-up graph GS2. Let's encode the random choices that we have. Let's encode them by a vector of plus minus 1s, where we have a plus minus 1 on each edge of the original graph. And plus 1 means that we will replace the edge by 2 parallel edges, and minus 1 means that we replace it by 2 crossing edges. Okay, I hope you remember the operation. So now, given this vector S, what happens to the eigenvalues? Maybe it seems complicated at first, but actually it's pretty simple. So the eigenvalues of the new graph are exactly all the eigenvalues of the previous graph. They just stay there, plus a new set of eigenvalues, which are exactly the eigenvalues of the signed adjacency matrix. We take the same adjacency matrix, but we put a plus 1 or minus 1 for each edge, and this is exactly the sign encoding what happens to that edge in the blow-up operation. But this is pretty easy to see, because you can take any eigenvector of the original graph, and either you just duplicate the coordinates, you put the same value on each of the new vertices, or you add a minus sign to one of the two clones. So this produces 2 vectors, which are actually orthogonal. When you look at the eigenvalues, these will just inherit the eigenvalues of the previous graph. And these eigenvectors, these will be the eigenvectors of the matrix AS, the signed adjacency matrix. So these will produce the new eigenvalues. So we assume inductively that we started with a Ramanujan graph, and so far things have been fine. So the eigenvalues of the previous graph are fine by assumption, but the goal is to see what is happening with the new eigenvalues, the eigenvalues of the signed adjacency matrix. Right? So that's the goal. Any questions? So far, pretty clear. So,
look at how you fill in the sign. You fill in the sign because for every edge you have a plus or a minus. So how
this is on the vertices. These are coordinates of the eigenvector on the vertices. So I will just copy them and...
Oh, for all other copies you do a minus sign? Is that?
So I take an eigenvector from the previous graph. I will copy it to the new graph. But then for each vertex, which became 2 copies, I will flip the sign on one of the 2 copies. And it's easy to see that when you apply the signed adjacency matrix to it, this will be an eigenvector. Oh, sorry, this should be the eigenvector of the signed adjacency matrix. And when you arrange the signs like this on the new graph, then it will be an eigenvector of the adjacency matrix of the blown up graph. Yes. Yes. So
one way to view it is if you restrict to odd functions, for every vertex you get 2 copies. So you get a subspace of even and odd functions. And the restriction of the operator to the odd function.
So these are 2 orthogonal subspaces, and yeah, we get 2n. Oops. Sorry. Yes, so we get 2n eigenvectors and 2n eigenvalues. Yeah, sorry about that. So yeah, so it boils down to analyzing the eigenvalues of this assigned adjacency matrix. So here are 2 classical results, which seem very helpful and suggestive of what should happen somehow. So the first result is that when you look at the signed adjacency matrix, you look at the characteristic polynomial. So that's the polynomial whose roots are exactly what we care about, the eigenvalues. But now let's take the expectation over all the possible signings. So we have, if we have m edges, we have 2 to the m possible signings of the edges. And the characteristic polynomial depends on the signing. So let's take the expected characteristic polynomial over these random signings. This theorem says that that happens to be exactly the matching polynomial that we talked about earlier. So that's interesting. It's actually the matching defect polynomial, which I defined earlier. But that's nice. And we also have a theorem of Heilmann and Lieb, which talks about the roots of the matching polynomial. And it tells us that for a deregular graph, the maximum root of this matching polynomial is guaranteed to be at most 2 square root d minus 1. So it looks like there's something happening here. This cannot be a coincidence. This is exactly the bound that you would like to obtain. And this says that the expected characteristic polynomial has roots bounded by the bound that we want, exactly the expression that we want. So I wonder what Nikhil et al. Were thinking when they saw this, but it's like this must work, right? But something doesn't add up. So what doesn't add up? The roots of this expected polynomial in general don't have anything to do with the roots of these individual polynomials which are sitting in here, right? In general, if you take some family of polynomials and just average them, take their average, and you say something about the roots of this average polynomial, it might not have much to do with the roots of these individual polynomials. In general, this is not true. There's something very special about this family of polynomials which actually makes that true, which makes it work. And that's the magic of interlacing polynomials. So what are interlacing polynomials? This is a picture similar to what I showed in the first lecture. There's a little difference here. Here we have 2 polynomials of the same degree. So for 2 polynomials of degree n, we say that they have a common interlacing if we can place these markers on the real line, gamma 0, gamma 1, and so on, such that the ith roots of the two polynomials, respectively. Alpha I and beta I are the ith largest roots of f and g, are sitting in the same interval, gamma I minus 1. So when you look at the picture, between every pair of consecutive black points, you see a red root and a blue root. Okay, so somehow the two polynomials are oscillating up and down in a consistent manner, you could say. That's what we call having a common interlacing. Okay. So here is a very nice alternative equivalent way to express this property. Two polynomials, two monic polynomials, which means the leading coefficient is 1, have a common interlacing if and only if every convex combination of these two polynomials is also real rooted. Okay, so the picture shows what is happening here. The blue polynomial and the red polynomial have a common interlacing. And the claim is that this is the same property as every possible convex combination of the two being also real rooted. So let's see why this is true. So this has two directions. One direction, let's assume that the convex combinations are real rooted. Okay? Let's assume in addition that f and g don't share any roots. This is a technical assumption. We can do it without loss of generality because if they share some roots, we can just take out those roots. Remember, we can break down the polynomial as a product of factors, and these polynomials would share some x minus lambda j factors. So just take them out, forget about them. So now think about what happens when we move continuously from one polynomial to the other one. Like we move t from 0 towards 1, and we can track the polynomials of this intermediate polynomial ht as they move on the real line. So now actually it's useful to have the fact, which was an exercise after the first lecture, which was that if you change the coefficients of the polynomial continuously, the roots move continuously in the complex plane. Well, now we assume in addition that all these intermediate polynomials are real rooted. So actually the roots, they move continuously on the real line. Right? They're not allowed to escape to the complex plane. So as you move t, each root, let's say the ith root or jth root, will move from lambda j of 0 to lambda j of 1. So we have these intervals, lambda j of 0, lambda j of 1. The claim here is that the interiors of these intervals actually have to be disjoint. They cannot overlap. Also, you cannot have a larger interval like containing a smaller one. Or in other words, inside this interval, lambda j 0 and lambda j 1, you cannot have another root of one of these two polynomials. And why? Well, that's exactly because we are not allowed to have shared roots, or because we actually eliminated them. Because what would happen if you had another root in this interval, let's say lambda k of 1, which would mean that would be a root of f. Lambda k of 1, if it was inside this open interval, well, then it would mean that, for one thing, it's a root of f, but also it's a root of this intermediate polynomial ht for some t strictly between 0 and 1. And that would imply, because this is a non-trivial convex combination, it will also need to be a root of g. So it would actually have to be a root of both f and g. But we took out all the shared roots, so this cannot happen. So this is a contradiction. So actually you cannot have another root. It can never happen that these intervals overlap, that the interiors overlap. They might touch at the endpoints. That might happen. But these intervals are disjoint, except for the endpoints. So they are ordered on the real line, just like in the picture. And this means that f and g have a common interlacing. Right? We can put some black points to separate this interval. The black point could be on the end point of the interval. It could coincide with the root. That's allowed. That's fine. But we can find this common interlacing.
Right. When you say lambda j 0, you really mean infimum of all the lambda j's over t, and lambda 1 is the supremum.
Well, no, actually in this proof I mean the starting point. Lambda j of 0 is simply root of g, I guess. You can also prove that the root is actually not allowed to leave that interval. I think I didn't even need that explicitly in this proof, but it's also true that as the root moves from from f to g, it cannot leave the interval and come back, because again, that would mean that, let's say, the root of g was identical to a root of one of the polynomials ht somewhere in the middle, so that also cannot happen. So, yeah.
It's not necessarily monotone, but it's...
Doesn't have to be... It doesn't have to be monotone.
The extreme points are 0, are given by 0.
Yeah, yeah. I think it might... It should be actually monotonic, right? It should move monotonically, but I don't need it here, but I think like it cannot go like this. But then I think you could find two non-trivial convex combinations where the roots coincide, and that would also imply that there's a shared root of that dimension. So I think that's also cannot happen. All right. The other implication is actually one of the exercises. So let me skip it. The corollary here, which will be very important, is that if f and g have a common interlacing, and you look at one of these intermediate polynomials, ht, maybe the average of the two. Let's say it has a maximum root mu. But as the picture suggests, this maximum root of the gray polynomial is actually between the maximum roots of the blue and red polynomials. So one of the two, either blue or red, must have a maximum root which is at most mu. Formally, you can also say that you can actually design the common interlacing to be such that gamma 0 and gamma 1 are exactly these two maximum roots, the maximum root of the blue polynomial and the maximum root of the red polynomial. And because the gray polynomial is consistent with the same interlacing, its maximum root is somewhere in between. We will actually use this conversely. We will know something about the maximum root of the gray polynomial, and from this picture at least, it's obvious that one of the two maximum roots of f or of g must be at most mu. They cannot be both above, because the maximum root of the gray polynomial is between them. So this will be very important. That makes sense? We already proved that f and g have a common interlacing if and only if all the convex combinations are real rooted. And from this proof, it also follows that the gray polynomials they are consistent with the same interlacing points. So the gray polynomial actually must be such that its maximum root is between gamma 0 and gamma 1. The picture is suggestive, but this is also questions about it. This is a critical argument in the proof. And with this property, we can formulate the method. The method of interlacing polynomials at a high level is the following. So we have some family of polynomials, let's say indexed by s. S consists of m parameters. Let's say just plus minus 1. It works even more generally, but let's say the choices are just binary, plus minus 1. So one polynomial is the expectation over all s, just the expected polynomial overall. That's the polynomial that we know something about. If you recall, that happens to be the matching polynomial in our situation. And then we have these intermediate polynomials where we have fixed a number of choices. We have fixed, let's say, the first k choices, s1 through sk, are already fixed to be plus and minus 1s. And we take the expectation only over the remaining choices. So now, the argument of Marcus, Bielman, and Srivastava is as follows. Start with f empty set. And we already know that its maximum root is bounded by what we want. It's bounded by 2 square root d minus 1 because it's a matching polynomial, and we know that that's the case. So the maximum root is well behaved. Now we have two choices for S1. Right? We are deciding to set S1 to be either plus 1 or minus 1. And by the argument on the previous slide, the polynomial f empty set is a convex combination of the two polynomials where S1 equals plus 1 and S1 equals minus 1. So its maximum root is somewhere in between the maximum roots of these two guys. So for at least one of these two choices, the answer must be yes. The maximum root is still bounded by 2 square root d minus 1. So this is, it's in some sense an algorithm, except this is not implementable in polynomial time like this. But you can make this sequence of choices. You check these two, the answer is yes here, so set S1 to be equal to plus 1. Then ask about the next variable, S2. Should it be should it be plus 1 or minus 1? Again, check the maximum root. One of them must be at most 2 square root d minus 1. You can continue like this. And what is important, when does this work? It works if at every step the two relevant polynomials have a common interlacing. But we still haven't proved that part, right? We don't know that. So if it's true that at every step we have two polynomials which have a common interlacing, then we can invoke the argument about the maximum root, and we can argue that one of them must have a bounded maximum root. Does that sound good? So what remains? What remains is to...
I'm sorry. Yeah, so
yes.
The reason it cannot be immediately implemented because it's hard to figure out the roots of all these.
Yeah. So.
That's
Yeah.
only
So how would we compute the roots? There has been an effort to do that. I think Cheyenne has worked on it. So for one thing, these polynomials are they're averages over exponentially many polynomials, and then you have to compute their maximum roots. So that's not easy. You can approximate the maximum roots in certain ways, and you can get some approximate results from that.
But the error will be like building up, right? The error will build up, right?
The error will also build up, yeah. So you can analyze this, and Cheyenne has a paper with Nima, Anari, or with Nikhil. Yeah, who are the authors?
Nikhil, Nima, and me.
So they have a paper where they do this very carefully using smart methods, using Chebyshev polynomials and whatnot, and they achieve a running time of 2 to the cube root of n, right? So you can do something non-trivial, but it's still, that method is far from being well run.
Yeah, right. I mean, maybe the immediate thing is the reason you can't compute them exactly is just because the last coefficient is the permanent. So like, I mean, even the polynomial at the root, the matching polynomial, the last coefficient is...
You cannot compute the coefficients. Yeah, exactly. Right. The methods that they use actually don't require all the coefficients, right? It's only some sequence of coefficients, but yeah, we don't have these polynomials explicitly available. That's the first reason. So, yeah.
Sorry, one other thing, I think it wasn't clear. The Cohen's method doesn't make this.
Right. Very good. Yeah. So it was a follow-up paper of the same authors where they did the whole thing a little bit differently, and they obtained a stronger result that not only you have infinite families for every degree d, but you actually have a Ramanujan graph for every d and every n. So that was paper number 4, I think, right? And roughly speaking, it was that method which Michael Cohen made algorithm. Is that Reasonable? Yeah. So, all right, so this is the high-level description of the method, and what remains to be proved is that at every step, the two relevant polynomials have a common interlacing. As you recall, we had a lemma saying that one way to prove that two polynomials have a common interlacing, that you prove instead that every convex combination of the two polynomials is also real-rooted. So MSS actually proved the whole thing in one elegant theorem, which says that all these mixed characteristic polynomials are in fact real-rooted. So what exactly is happening here? So we had these polynomials x sub s, where s is a plus minus 1 vector, which corresponded to the way we do the blow-up operation. So now let's take a convex combination of these exponentially many characteristic polynomials, where we do the convex combination under a product distribution. So you can imagine that you set each si to be either plus or minus 1 with certain probabilities. These probabilities just interpolate between plus and minus 1. So we can generalize the notion of x sub s to x sub certain numbers between plus and minus 1, and we get this mixed characteristic polynomial. The polynomials which appear in the interlacing polynomials method are polynomials of this form. We already fixed the signs up to a certain point. We fixed the first k signs, and the remaining ones are random. They're half. Well, I shifted it. So, yeah, actually this should be 0. Yes, I shifted the range after. Yeah, good. Thank you. So 0 means that it's an unbiased choice, plus minus 1. Yes. And in fact, you can plug in for sk plus 1, you can plug in anything between plus and minus 1, which will get you all these convex combinations of the two relevant polynomials. So all the gray polynomials, they're of this form. So this master theorem, master stability statement, tells you that all these polynomials and many others are actually real-rooted. Okay, so what they prove is actually something even a little bit more general. It's the following kind of statement. So take independently random vectors. Each of them can have some distribution. Let's say supported on two choices, but that's not even very important. What we need here is random vectors, each of which has two possible choices. And they're independent. That's important. And we look at this expected characteristic polynomial of the matrix, which is formed by the dyadic products of these random vectors. So these are random rank 1 matrices. And that seems to be the important element here, that we have a matrix which is built up by random rank 1 updates. The randomness is independent between these successive choices, and each of them is just a rank 1 update. So that seems to be at the core of this method. And MSS prove that any polynomial in this form is actually a real root. So we can obtain the previous theorem from this one quite easily. If you remember, the relevant matrix in the previous theorem was the signed adjacency matrix. So what is the signed adjacency matrix? It has pluses and plus ones and minus ones for edges. It has 0 on the diagonal, so that's not very convenient. So it's actually convenient to shift it by d times the identity. You create the degrees on the diagonal, and you make it look like the Laplacian. Then you can express the matrix as a summation of these rank 1 matrices. So for each edge, you put down a certain vector, which is the indicator of one vertex plus the appropriate sign times the the indicator vector of the other vertex, and then the same vector transpose. So this will create exactly the 4 tuple of entries, +1, -1, -1, +1, or depending on what the sign of that edge was, you will produce that 2 by 2 matrix that you want, and if you add them up over all edges, that's exactly the matrix that we want. So we can express DI plus AS can be expressed in this form. So the choices here are just plus -1 independently and 50-50. But this theorem is much more general. So here's what you can say, actually, more generally. You can say for any collection of independently random vectors, if you know the maximum root or a bound, upper bound on the maximum root of this mixed characteristic polynomial, this matrix obtained by random summation of random rank 1 matrices, then there exist deterministic choices for these random vectors. For each of them, there exists a choice, such that when you look at this characteristic polynomial, this is an actual characteristic polynomial of a matrix, then the maximum root of this is also upper bounded by lambda 1, the same bound. And the proof is exactly what I described, the sequence of choices where in each step we look at the polynomials where some of these choices have been already fixed, the remaining ones are still random. We look at the expected characteristic polynomials over the remaining random choices. And again, we have the property that the two relevant polynomials where we fix the next choice to be either this or that, assuming that we have two choices for each. It works actually more generally. But if you have two choices for each vector, then the two relevant polynomials have a common interlacing, and therefore, for one of them, the maximum root must be upper bounded by the upper bound for the convex combination. So the upper bound propagates through the procedure, and you can one by one fix these choices until you have deterministic choices for all m vectors, and the maximum root of this characteristic polynomial is still upper bounded by the same thing. So this is a very general procedure which is also useful for the Cadison-Singer problem. All right, so I think that's all my slides. Did we hand out the problems? So we will take a little break. 10 minutes, 15 minutes, 10 minutes, 10 minutes, yeah. Very convenient.